Today we're going to finish off by just looking at a little bit more about fragmentation patterns. And then basically we're just going to start applying that, well, applying it, looking at examples of different molecules and how they fragment. And what you'll see is that it's not always as simple as we hope it will be. Some of these I tried to pick I tried to pick reasonably simple examples that could be explained just by the fragmentation mechanisms that we're going to talk about or that we are talking about, but it seems like there's always something else that more complicated that takes place. So let's finish off where we did last time. I had meant to insert that last slide that we had been working on in here, but I forgot. So I'm just going to I'm just going to add a new slide here. And what we were talking about, dang it, rearrangements. Okay. And I think we finished, well, let's just look at another example. I think what I showed you was kind of the generic mechanism for what will lead to this McLafferty rearrangement. So let's just look at a slightly more specific example. So if we had a ketone or carbonyl, what we're going to look for in order for this type of rearrangement to take place is that we need to have a proton on the gamma position. So if we count alpha next to the carbonyl, beta, gamma. So we need to have at least one proton at that position. Okay? So when a ketone like this is ionized by electron impact, it's going to ionize on the non-bonding electrons on the oxygen. Right, so I'm just going to go ahead and draw that so we'd have a molecular ion that looks like this. All right, so the first thing that can happen in this pathway is that a hydrogen atom at that gamma position gets transferred to the oxygen. Right, so we can draw this like this. So this electron combines with one of those electrons to get a hydrogen atom migration, and that electron goes onto the gamma position. We do that. We still have the plus on the oxygen, but we have a radical now at the gamma position. Okay? So, what's happened to the mass so far? Nothing, right? Because all we've done is move a hydrogen from one position to another, so the mass is still the same. So, the way that the cleavage usually goes is now a radical initiated, so an alpha cleavage that goes like this. That radical can go down there, combine with that to form a pi bond, and we cleave this bond right here. Okay, so what we get out of this then is another odd electron ion. Okay, we start with an odd electron ion. Remember, that's what we get for our molecular ion. Usually, when we, see kind of normal cleavage pathways, we get fragment ions that are even electron ions. Right? So another way that a ketone like this could cleave would be you know, the normal kind of non-rearrangement, this is the normal alpha cleavage. So we're just kind of contrasting. So this would give this plus the radical. Okay, so this is called the acylium ion. Right? And notice in this case we're going from odd electron ion. What about that acylium ion? Is it odd or even? Even, right? So there's an even electron ion. So let's think about how the masses would change then. So there's no nitrogen, right? So the molecular ion would have an odd or an even mass. Even mass. And what about the odd electron fragment ion? Over here. Well, what did we say? If we have an odd electron ion with an even number of nitrogens, is it going to be an odd or an even mass? An even mass. Okay, so this is more unusual, right? So down here, remember, we're going to start with an even mass. And if we go to an even electron ion with no nitrogens, then this is going to be an odd mass. All right, so if we're looking at a mass spectrum of a molecule that has no nitrogen, usually all the fragment ions are going to be odd masses. Okay? However, if a rearrangement takes place where we break more than one bond and or if a hydrogen gets transferred, then we can get an odd electron ion as a fragment ion. And so that's going to tell us something. It tells us that this has to be a functional group that can do a rearrangement, something like this, perhaps. Yeah?
The first rearrangement that we talked about, that was a gamma rearrangement?
Yeah, gamma. So that's called the McLafferty rearrangement. McLafferty. Okay, so this can happen with different kinds of carbonyls as well. And let me just show you one more example. Is it can actually happen from benzene rings. If we have alkyl substituents. Something like this. So again, we could count this as alpha connected directly to the functional group, to the benzene ring, beta, gamma. If we're going to draw the ionization in a benzene ring, what we can do is we can knock out one of the electrons. Of course, this is all going to be delocalized within the benzene ring, but if we want to draw a fragmentation mechanism, we kind of draw it with those, with the electrons localized. Okay, so if we draw it, we've knocked out one electron, so I'm going to draw it like this with a plus at that position and a radical at the adjacent position. So all we've done is kind of knock out an electron from that pi bond. Okay, so now we're kind of set up to where we can transfer a hydrogen atom over to the ring. Okay, so it's the same step as what we saw up above for the carbonyl. Okay, so this this radical. There's now 2 H's. So we have an sp3 hybridized position on the ring. Okay, now just like before, we can do an alpha cleavage from that radical. So a radical initiated cleavage. This can go down here, can combine with one of the electrons from the adjacent bond and cleave that position just past what used to be the benzylic position. Like this, plus a neutral alkene. Okay, so again, if we start with an odd electron ion here as our molecular ion, we end up, in this case, notice that the new ion, the final ion over there has a radical and a plus, right? So that's an odd electron ion. All right, and so if we're going to go from an even mass, we would end up with another ion with an even mass. In fact, this mass is at m over z equals 92.
He always mentions
That's he was talking about asking about the tryptylium line.
Okay, that's like 91.
It's 91.
okay. Does this specific fragment have a name?
Not that I know of.
Okay.
All right, so these are a few of the rearrangements. There's other rearrangements that can take place as well. I think we'll look at a couple today as we go through and try to figure out some of the spectra that I have in the examples. All right, so just a few general rules then. Well, and about the spectrum in general. So the relative intensity or height of the molecular ion is greatest for straight chain molecules. Okay, because especially for alkanes and things like that, because none of the ions that you would form are going to be very stable, right? They're all going to be primary carbocations, are not that stable. And so the relative height of the molecular ion is therefore going to decrease, not therefore really, it's going to decrease with increasing chain length. Okay, I think there's just more ways to fragment then. And cleavage is favored at alkyl substituted carbons, right? Because if we have some, chain like this, it's going to be favored at positions adjacent to where the substitution is, because that will give a more highly substituted, a more stable carbocation. All right, double bonds, rings, or aromatic rings all stabilize the molecular ion. All right, so the molecular ion would be more abundant. Okay. If we have cyclic alkenes, they favor, so if we had, let's see here, a cyclic alkene like this, if it were to ionize, it would ionize on the pi bond, and we could draw it then with a radical on one side and a cation on the other. All right. Then, in order to fragment, the ring actually has to open. And so we can do kind of cleavage like this, radical initiated cleavage of the ring, which is going to give us an allylic cation. And then, just like with the McLafferty and those kind of things, it can then do another radical initiated cleavage. And in this case, it is going to form an odd electron ion, because we had to cleave, we haven't transferred a hydrogen, but we've had to cleave 2 bonds in order to yield our fragment ion. So this is an odd electron ion over here. Another way, let's see here, saturated rings lose alkyl side chains. Yeah, so saturated rings, if it's a methyl cyclohexane or something, it'll lose the methyl group, right? Because that just gives, that kind of follows what we did up on number 3. And the other kind of cleavage here for that cyclohexene is that it can do kind of a retro Diels-Alder. So if we ionize like this, so let's say that we're going again from this down to here, I think we can kind of push electrons all the way around this way, like that, that, and like that. And what we end up with then, if we follow all those arrows, we've cleaved this bond and this bond, and we end up with an alkene here. Well, that's kind of what we did up above.
In one step.
Same thing, but we just did it in one step. Yeah. So that's kind of formally a, remember, a Diels-Alder. You guys remember that reaction? Yeah.
Can't forget it.
Yeah. Good. More things. Okay. When we have substituents on benzene rings, the way we can show the cleavage is that first we'd ionize, and again we do it similar to what we did on the other one, but this time I'm going to draw the radical at the position of the attachment. And then we're just going to do another one of these alpha cleavages. So this is going to go here. I'm going to cleave this other bond like that. And so this is going to give us this and this, right? And this is the favorite, can rearrange, I'm not going to draw all that out, can rearrange to this, let's see, put one more in there, right? 7-membered tropylium ion. Tropylium, however you spell that. I'll just write it real sloppy so we can. And this is at M over Z equals 91.
And will be the base peak. Right?
Yeah, if we have a substituent like that. So for benzenes, important ions are this one, tropylium at 91, or if we can go just to the benzene ring is at 77. Let's see, carbon-carbon bonds next to heteroatoms are frequently cleaved. So this would be the heterolytic cleavage. So if we had, you know, something like this, we'll see some examples like this. So the heterolytic cleavage, remember, is where the electrons adjacent to that heteroatom move towards the plus. And so we end up with a plus here and a radical. No, not, that's wrong. Sorry. Plus doesn't stay there. We get a radical on that's on the oxygen side and a plus on the other side. And the last thing, I think the last of my list, cleavage involving loss. Cleavage should involve the loss of small, stable, neutral molecules. Loss of carbon monoxide or alkenes like we've seen, loss of water you can see sometimes, loss of alcohol. So some of these take rearrangements to lose these stable small molecules. All right, so let's just look at some examples. Mm-hmm.
Does this only apply still to electron?
Yeah, we're only talking about electron impact.
So these rearrangements may not necessarily occur in other techniques.
With other ionization methods, because if you don't generate the same type of ion, right, then the fragmentation patterns are going to be different, right? Because if you're ionizing just by protonating a molecule, right, to form a cation, then you have no radical. And so radical mechanisms are not necessarily going to be favored, right? They would all be more cation initiated, you know, mechanisms.
Okay.
All right, so these are just kind of back to some of the, starting with simple ones, though I'm still not 100% sure why it is that for this, so this is just decane. 8, 9, 10. Okay, the molecular ion is out here. I think that's at 132. And the main thing that we see, you know, is just these differences in 14 mass units. All right, and the reason is just that as we cleave along this chain, you know, if we cleave and lose the long piece, we're going to have the possibilities of 43. Right, the next bond, if it was cleaved, would be at 57. Then we could go up to 71. And so, you know, we only have discrete places that it can be easily cleaved. When we put some type of branching in the molecule, then we see a different pattern or different Right, so this is 4-methylnonane, so it still has the same molecular ion, but it really didn't, when I was starting to look at this again today, didn't really have necessarily the base peak as one that seemed like it would be the most, you know, the easiest to form. Because if we take this, we'd expect it to cleave around the branch point. Okay, so This starts at 130, 142. Maybe I was wrong on that last one. If we lose a methyl, right, then it should lose 15. Should go down to 127. And we maybe see a tiny one at 127. If we cleave on this side, and we lose a propyl group, right? So we'd lose 43. That should give an ion at 99. And it might, I don't know if it's the big peak there. It looks like the smaller one there. 99. If we cleave at this other branch point, then this would go down to 71. Okay, which is right here. Right, but we haven't actually gotten to the base peak. So I guess what's happening, I guess either we're cleaving here and the cation is going to the small piece, to what would seem like the less stable one, or we can also, though I think this is not what we usually talk about, is that it can also do some sequential cleavages too. So if we form, say, a cation like this, then we can have these electrons go like this, and we form a new cation and then a neutral alkene. So we form the alkene, and then this would also be at 43. So it may be that there's just more ways to form 43. Well, that's not even 43. The next one is 57.
So maybe it's fragmenting still. But
Oops, sorry. Yeah. This is 43. So 57 would be the next one up, right? So I guess we could maybe go from 71, if we lost 28, you know, another ethene, then we would go to 57. All right, so we're not using alkanes, though. And the cleavage, you know, is usually more predictable when we have, well, I guess those are probably predictable, but if we have functional groups. Okay, so this is 2-ethoxybenzene, not benzene, butane. So like this. All right, the molecular ion is at 102. Notice it's very small, right, because there's easy cleavage mechanisms. All right, so we're going to ionize on the oxygen. Okay, so we're going to end up with a radical cation on the oxygen. And then we can do either radical-initiated cleavage or cation-initiated cleavage mechanisms. Right? They're all going to be competing with one another. So, for example, we could do, you know, the alpha cleavage ones, the radical, are like this, remember? So, for example, that one would lose a methyl group, right? So we'd end up with this, the plus here, and this should be at 87. Okay, here's 87. So it happens a little, but not that much. All right, we can do the same thing, but go in the other direction.
That methyl group, we just didn't show because it's not going to be.
It's not going to show up, right? So it would be a loss of a methyl radical.
The radical doesn't show up.
Right, we only see the cations. Okay, we could also lose this methyl group, right? Just pushing it the same way, and cleave this methyl group. Or we could lose this ethyl group. Okay, so we could draw this. I'll draw this in a different color. This will go down here, like this, and like this. This would give us O plus, like this. All right, so this is plus an ethyl radical. Right, so this should be minus 29, and so that's going to get us to 73. Right, minus 29.
Does it see
The ethyl, right? We should get
Something seems odd here.
methyl group connect to the.
Oh, there's a methyl group there.
Only methyl.
I stuck in a. That's. Oh, I
And the other
screwed
side
it all
should be-
up.
And the other side, there should be nothing connected, yeah. That's it.
There. And there should be an H on that side.
Yeah.
All right, so that's 73. Now, so those are just the radical initiated. I'm going to redraw the structure over here. All right, and then we could also do the cation initiated reactions, which would be one going this way. Right, and that's just going to give us, oops, an ethyl cation plus the oxygen radical. So that would be at 29, which we might see right here. And if we do the same thing the other way, then we get this butyl cation plus this radical. And so that is at 57. So here's 57 down here. All right, so we've kind of gotten almost everything except for the base peak, right? Which the base peak is the one which really would be the best to see. And so what can happen is that we can get a further kind of rearrangement. So let me see if I can follow these from my notes. The way that these work is we can start 87. Okay, we can start, let's start one from here up at 87. I'm going to just put on this H that's alpha beta. Is that the right one? No, well, no, that's not the right one, I don't think. I'm going to draw this other one over here. So the way they draw this is that this hydrogen gets transferred over to the oxygen, and then this bond breaks. It's not how they draw it, though. I was kind of struggling to kind of follow this. So this, I'm going to have to go way over here because I'm out of space. So if I did that, oh yeah, I guess that's right. So they show it like this, cation like that, plus, I guess we lost this alkene.
But we still first had the red, right? This is just a two-step. We had the first.
Right, so we first had the ion at 87,
Mm-hmm.
and we observed that, a small amount, and then that further fragmented. But this one isn't really where I wanted to end up. But let's see, this would be 14, 30, this would be 31, I believe, which is really small right here. But we should be able to get to, from 73, from here. We do the same thing. I know these are, I just had to come up with the, a way to understand the base peak. Okay, then we transferred the H over here. We get this plus the alkene. And I believe that this one is at 45. So this apparently, and I'm not quite sure why this, if this is how it's formed, this kind of double cleavage is the base peak. So we go from 73 to 45. We went, I think there's a way also to go from 87 to 59. So 87 could also follow that same type of pathway to get to the 59. And we also generated 31. So I think these are a little bit, I'm not quite sure why that one is so big. But I think for me, if we can understand more these radical initiated and cation initiated fragmentations, then that's pretty good. But this rearrangement is a little trickier, I think.
So Dr. Davidson,
Yeah.
when doing a problem like this, we don't just start drawing out different fragments that we think we could see match corresponding MZ numbers. We draw out radical cleavage and then cation.
Yeah, well, what I usually do is, what I'd like is to have some type of, well, what I would usually do is start with a molecular ion. Hopefully we can get, along with maybe information from NMR or something else, or IR, we can get a molecular formula.
Mm-hmm.
And then I would start by looking at what losses we see that are common. If we see, a loss of 15 or loss of 29, or, those are easy losses to interpret, right? Loss of methyls or ethyls, things like that. If we see an odd electron fragment ion, so we don't have one really in here, because as we look from 102, all of these big ions are all odd masses. So we know that they're all generated, by even though they have rearrangement, I guess it's because they're all generated just by a single bond cleavage. So we go from an odd electron to an odd electron, and then even though we rearrange, we then stay the same, right? Odd to odd. If we do a rearrangement from the starting point, then we go from an even mass to an even mass. Okay. So yeah, I would try, first look at the molecular ion, then look for those easy losses, and then as you start to build up your structure, then look for other types of fragmentation that you might expect. Or if you get to the point where you have several possible structures, then you might be able to use the mass spec to, select between those, because you could predict how each one might fragment and one might fit the data better than the other. Just like in NMR, right? We draw some different possibilities, we kind of predict what the spectrum would look like, and then we see if it matches or not. All right, so let's keep going. They're not all this tricky. All right, so this is ditert-butyl ether. So, oops. Like this. The molecular ion of this should actually be, I think, at 130. So we're not seeing the molecular ion. Okay, so this is not. And this is at 115. And so we're losing 15 to get to that ion. All right, so how would we lose 15 from this molecule? Yeah, look at all those methyl
Look
groups.
at all those fingers.
So we can just draw this alpha cleavage, right? On any of those methyl groups. And we get this, which is at 115. Okay, another obvious way to cleave would be the cation initiated. And it would cleave like this. Right? And that would just give us this kind of isobutyl cation, which is at 57. Okay, so this is 57. This is at 115. So I'm not exactly sure, again, how that 59 comes up. So it would have to do something else. But at least we got the two biggest peaks this time. No, that was 57. Sorry. I said 57 and wrote 59. All right, so this is back to one of the spectra that we looked at before, right? When we were just saying, oh, what does presence of bromine look like? But we didn't know, other than going from 164 down to 85, how any of the other ions formed. Okay? So, just to get to 85, we need to have a mechanism by which we could lose the bromine. Right? And so that is likely to be just a cation initiated cleavage, right? Gives us a plus here, plus a bromine radical. oops, Br, bromine radical. All right, and then, that, could, so this is 85, and then like we saw before, this could fragment further, losing 2 carbons at a time. Right, so this could go down to here, plus this, and so then that goes to 57, I believe. It still doesn't go to 57. Oh, dang, how does that?
55 or 56?
Huh?
55 or 56 on the.
Oh, that's 55. If you look at where it hits on the spectrum right there. All right, so some of these other ones, though, like going to 35, 135, right? So it's going from 164 to 35 is minus 29. So if we're going to ionize, what we've said is we're going to usually ionize on the non-bonding electrons. Why is it cleaving clear down at the other end of the chain just to lose 29? And so apparently these can cyclize. Okay, so we can draw, I'm just going to draw this chain bent around a little bit here. Like this. One way that it can cleave is it can go with this bond right here and cleave that. And if we do that, we end up with, how many do we have there? Did I draw enough? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yeah. So, I should have drawn in one more into that ring that we're going to form. So let me do it like this. Like that. So then we're going to end up forming this, like a 5-membered ring plus an ethyl radical. So here's our loss of 29, and this ion is at 135. All right, we can also do it right here. And what that forms is the bromine. It's kind of a bromonium ion, like we would do during a bromination reaction, is a 3-membered ring. And we lose the butyl radical, and this is at 107 and 109. Okay, so those are right here. 107, 109. Apparently, just to keep drawing all these weird ones, apparently this 57, usually we'd think it would lose 2 and give us 29, but apparently it can also go like this. Let's see, like this. No, that's not what I want to do. What do I want to do? Oh, I'm going from the wrong one. I think from 85. Yeah, from 85. So it can actually break this bond. Am I doing this right? 85. Yeah, it's just cleaving the next bond. And if it did that, it forms the 3, so this one, which is at 43, plus a cyclopropane. And that, well, it may not have to form it just in that way, because we can make 43 in different ways, but 43 is actually the base peak, which seems to be the base peak whenever we have these long alkyl chains, right? Probably just making this more complicated than we need to, but I just, when I looked at these, I was just like, even though they were good examples for part of it, without being able to show a mechanism for to form the base peak. All right, so this is the other one that we looked at, but all we did was look at it for the presence of chlorine. Okay, so we saw this 3-to-1 ratio right here, and so it told us that there was chlorine in the molecule. All right, so I'm just going to draw up the structure, and we're going to try to come up with a couple of these big fragment ions. Okay, so here's the structure. Like this. And so let's first see if you can come up with a way to generate the ion at 107. Okay, so this is going to be a loss of... Right. Yeah, probably the chlorine with the CH2. Okay, so where is it going to ionize to do this cleavage? On the oxygen, yeah. All right, so if we draw it this way, that goes over to that carbon.
Can I ask you a question, Dr. Davidson?
Mm-hmm.
On your third red radical arrow,
Yeah.
are you pointing the end of that arrow to the carbon, or to
Yeah,
the
it's supposed
bond between the carbon and the chlorine?
No, it's supposed to go to the carbon.
So the other two are
Are
towards a bond.
yes.
And then that last one points towards a carbon. So that's
Yes.
where it ends up.
Yep.
Okay.
Yeah, sorry. I started going too wide and I tried to curl it back in there. Tried to save it, but I didn't do a good job. Okay, so this is at 107. All right, what about 94? Does that 94 have the chlorine in it?
Nope.
Nope. So what's unusual about it? Even mass, right? So it needs to do a rearrangement. So this is going to do essentially that rearrangement that I showed you with the benzene ring. Right, because it has an oxygen here, and then 2 carbons, and then the chlorine. Right, so if we ionize that like this, then we can transfer a hydrogen atom over to the ring. So we have a radical there. We have 2 hydrogens on this side and the plus. And then we finish this kind of McLafferty cleavage like that. Well, we didn't, oh yeah, we did finish it. And then we have a radical here, plus there. 2 H's, and this is at 94. Right, remember if it was an oxygen there, that's when we had 92. So that oxygen has 2 more mass units than a CH2 group. So what about 77? That's just the benzene ring. So we can draw that by doing this cation-induced cleavage just like this. This is at 77. All right. Okay. All right, this is just 1 hexanol. Has a mass of 102. So you're not really seeing it out there. Okay, so can you guys read these things at all, or do you have it? No.
Barely.
Yeah, this is at a 84, 102, 59. Is that 50? This is 56. 43, 31. 31. All right, so we're seeing a couple of odd electron ions. All right, so what about 102 to 84? Huh?
That's the loss of water.
Water, right? So it's loss of 18, so we're actually losing a water molecule. Okay, so the way this is usually drawn is, okay, I'm going to ionize on the oxygen and on the, well, it'd be better if I, here, let me I'm going to redraw this. OH, if we draw it so it's more like this. And this is the alpha, beta, gamma, delta position. Sometimes I've seen it to the gamma position as well. And so, again, a hydrogen atom gets transferred. And so essentially what we've done is made this water over here. Oops, that's a radical. And then it loses this water molecule. Oops, too many. Plus H2O. So this should be at 84. And then I think from here we can just do, oh, this is the radical over here. We can do this to lose a ethylene. And we generate 56. And I think that's enough. 31 was one of those ones that we did from the ether. So it takes one of those hydride or hydrogen atom shifts to get to there. So I think we only easily lose water for like these primary alcohols.
And the reason for choosing delta instead of gamma to assess
That's just what I showed is, well, I think it's because, you know, to reach around, you know, 6-member transition states are a good size of a ring, right? And so that's oftentimes the favored ring size to transfer an atom like that. Too many here. What do we have? 3-hexanol. Oops. Oh yeah, 3-methyl 3-hexanol. So we are, oh, here's the molecular ion is out here at 116. Okay, so we can easily lose 15, right? Here, just an alpha cleavage. We can lose ethyl, which would be to 87, right? Minus 29. So that's loss of an ethyl going this way. We can lose the propyl group, minus 43. Right? So all of those, you know, essentially are the same type of cleavage. We just have 3 different groups here. It ionizes like this. We go like this, and we can lose any one of those 3 groups, right? For example, this one. Okay, that one's caved. Same thing with this one. You know, we've got the ether here, where it can ionize. We can have, and this just shows the cleavage, so the ones out here, this and this, 115 and 73, these are the alpha cleavages. And the ones right next to the oxygen, those are the cation initiated, right? So 43 and 71. Right? And so we see both of those mechanisms when we have ethers or oxygen. Oh, this is the same one we already, I think I put it back in because I think the first time I did that one I couldn't explain some of those, and I came back the next day. Okay, what if we have an amine? Look at this long chain amine. It has a molecular ion of 185, right? Notice it's an odd mass, 1 nitrogen, but we see almost no fragmentation other than all the way down to 30. Okay, so how is that cleaving to give us 30? Yep, so this is just for these primary amines like this. It just does this alpha cleavage. and the predominant ion is just like this, 30, right, plus the radical. Amines do mostly the alpha cleavage. They don't do so much of the cation initiated because they're better at donating like this. They're better at holding this plus charge on the nitrogen, even better than oxygen is. One more example and then we can quit, and then we mostly have like problems to work out. Okay, so here's a ketone starting at 128. All right, if we do the alpha cleavage right here, we end up with this acylium ion, and this is at 43. I'm losing that big thing. So what about this 58? That's just the McLafferty rearrangement, right? All right, let's just quit there. I think this is an overload of all of these.
I need coffee.
Yeah.